Bismillahirrahmanirrahim. So our today's topic is energy in a simple harmonic motion. Now simple harmonic motion, let us try to understand this topic first. What is simple harmonic motion? We know that rectilinear motion is there, translational motion is there. Okay, in SSC level, while we were discussing the chapter motion, we got to know about several types of motion, right? If you remember, periodic motion, okay, circular motion. Then we studied one motion, if you remember, that is vibrational motion. Vibrational motion is just what is simple harmonic motion, okay, or it is called oscillatory motion. Now the example that we generally give, that is of simple pendulum. Okay, simple pendulum. This is the equilibrium position. From this equilibrium position, let us say I have hold this and brought it here, and then if I leave it, then what will happen? It will come here, and it will not stop here, right? It will come to some position like this, and then from here again it will go back, and it will go back to this position, and then it will continue the motion like this. Okay, so this motion is simple harmonic motion. What are the characteristic of this simple harmonic motion? In the definition, we can define it in such way that half of its time, it has a time period, right? Time period. What is this time period? Let us say it started from here, so it will go to this position and come back to this position. One oscillation has been completed, we will say. One oscillation. And for this one oscillation, we know that the time required is known as time period. So half of this time period, it will move in a particular direction, and the rest half, it will move in the opposite direction. This is how we can define the simple harmonic motion. Okay, half of its time it will move in a particular direction, and another half it will move in just the opposite direction of its previous motion. Okay, now some similar examples we can think about, right? Let us say I told you about tuning fork also, right? Okay, tuning fork that looks like an Y. So if you hit it, okay, with any object, let us say we have hit it, what will happen? It will start to vibrate from here. So as it is vibrating, can you see what is happening? Okay, let us say this is our tuning fork. I hit it here. I will hit it. Then what will happen? It will have some displacement. Then if I leave it, what will happen? It will continue this simple harmonic motion. So if you take a closer look, what is happening? It is starting from this point. It is going to that point and then coming back again to this point. One oscillation completed. Two oscillation completed. Three oscillation completed, right? So for one oscillation, the time that is required is time period. Now within this time period, what it is doing? Half of the time it is going in one direction, and another half it is going in the opposite direction, right? So this way we can define simple harmonic motion. There are some other characteristics about which we are going to know. Okay, see, if a force is acting on an object is directly proportional to its displacement. This is a very important characteristic. Okay, this one actually we got to know in case of a spring also, right? Because in a spring there is simple harmonic. Whenever you expand it, okay, it will go back, for a little bit amount of time, it will be in simple harmonic motion, then it will come to rest, right? Okay, so here what I want to tell you that the force is proportional to actually negative of the displacement. Okay, why it is negative? Because the force that is working on it and the displacement that is occurring is in the opposite direction. You see, when you want to displace it, you are applying a force to move in that direction, right? But the force within it, the generated force will be in this direction. It will feel a force always to come back to this position, right? Now the force that will be generated within the pendulum to come back to this position is proportional to the displacement. See, as I increase the displacement, more amount of force it will be felt over here by the pendulum to come back to this position. Okay, so as the displacement increases, the force increases to come back to this position. Okay, always from the equilibrium position, the displacement x is proportional to this force. Now why this is negative? Because the direction is opposite, or we can say that the force is in this direction, but we are causing the displacement in the opposite direction. So that is why they are opposite. Acha. So from here, what we can write? The force applied will be equal to minus kx, and here this k is known as force constant. Force displacement. Okay. Acha. So let me read the first line. If a force is acting on the object is directly proportional to its displacement. Force is directly proportional to its displacement and is always directed towards this point. এবং সব সময় দেখবে যে এই ইকুইলিব্রিয়ামের দিকে এটা চলে আসতে চায়। যখন এটা এটার দিকে আসবে velocity বাড়বে, but as soon as it crosses this point the velocity will decrease. That means it will show you that it has a tendency that it wants to come back to this position. So as soon as it crosses, as it is going away from it, the velocity will be decreasing and it will come to at rest at some position. Then again it will start going to that position, and till it is coming to that position, the velocity will be increasing. But as soon as it crosses this point, the velocity will start decreasing again, right? Okay, so we can see that the motion is always directed towards this equilibrium position. Okay, acha. Then it is called simple harmonic motion. The fixed point is called the equilibrium position. This point, okay, this point is fixed and this is called equilibrium position. Now the example they have shown in the book is a little bit different. Okay, they have considered B and C are 2 points and in the middle O is a point. Okay, so O is the equilibrium position. From O I have taken it to C, and then when I left it, it is in this to and fro motion. Okay, so O is the equilibrium position and C is one extreme position and B is another extreme position. I hope you understand what I mean through extreme position. Extreme position means the maximum displacement position, the point where the maximum amount of displacement is caused. Okay, acha. From the equilibrium position, the distance, this distance is actually amplitude. If you remember, we studied this in case of wave. This is the equilibrium position. From equilibrium position to a particular direction, the maximum direction covered, the maximum distance covered in a particular direction is amplitude. If I'm taking in this direction, then this will be also equal to amplitude, right? So likewise, from here to B, it will also be equal to A. Okay, amplitude. Acha. So that is why OB equal to OC is equal to A. OB is equal to OC is equal to A, as I have shown. The motion of a vibrating tuning fork, a fixing end of a spring at a rigid support and the object hung at the other end is allowed to oscillate. That means this bottom part I will rigidly fix it and this part I will allow to oscillate. Okay, so when I will hit it, it will be this part will be moving, this part will be rigidly attached. Achha, so this part will be in simple harmonic motion. If a force applied on a particle F and the displacement is x, in case of simple harmonic motion, F equal to minus kx, as I have shown here already. Here k is a constant and it is known as force constant. Okay. The potential energy of a particle executing simple harmonic motion at a distance x from the equilibrium position is half kx square. This one we know from the spring. If you remember, the work done was half kx square. The amount of work done is equal to the potential energy that will be stored in the body. So we can say that this is the potential energy that is stored. Okay. See, whenever there is a simple harmonic, a simple pendulum, and you cause it to have some displacement, definitely you have done some work for taking this object from here to here, right? That amount of work will be stored as potential energy in this object, and that is half kx square. Okay, acha. Now if the velocity of the particle is v, let us say at any point the velocity of this object is v, then we can calculate the kinetic energy as half mv square. Okay, so we got our two expression for whenever we calculate potential energy, we will use this expression half k x square, and whenever we will calculate kinetic energy, we will use half mv square. Okay, now let us see. Okay, the velocity at one end of the oscillation at c, when the one end, it means this is b is one end, c is another end. So at this point, what is actually happening? If you remember, in case of pendulum, as I showed you, from the equilibrium position, when it goes to one end, the velocity is 0. From there it starts moving. Okay, the velocity is maximum at the equilibrium position, and after that the velocity starts decreasing, right? Understood? See, the velocity is 0 over here. It is not moving. Then I leave it. It starts moving. Velocity increase, velocity increase, velocity increase, maximum velocity. Then velocity decrease, 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 and the velocity is 0 again. At this extreme position, again the velocity will be 0. Then again the velocity increase, 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 and maximum velocity, and velocity decrease, 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 0 velocity. Understood? Do you understand the situation? তোমরা কিছু রেসপন্ড করতেছো না আসলে।
Yes, sir.
ওকে, এটা তো আমরা ইমাজিন করতে পারি না যে পেন্ডুলামের যে মোশনটা সেটা দিয়ে। তো তাইলে এখানেও আসলে জিনিসটা এরকম হবে, যখন সি পয়েন্টে যাবে ভেলোসিটি 0 হবে। দেখো তো এই সি পয়েন্টের জন্য হোয়াট ইজ ডিসপ্লেসমেন্ট? ডিসপ্লেসমেন্টটা আমরা x দিয়ে রিপ্রেজেন্ট করি না। তো x এর ভ্যালু ইকুয়াল টু হবে a, because from the equilibrium position I am at a distance. So x is equal to a, and what is the velocity? The velocity is 0. This is for position.
0.
Now at position C, if I want to calculate the potential energy, I will have to use this expression half kx square. Now we know that x is equal to a, so it will be half ka square, replacing x by a. And what will be the kinetic energy? As we know that the velocity is 0, half mv square is 0 square, so it will be 0. Now if I ask you to calculate the total mechanical energy, then total will be half k x square plus 0 is equal to half k x square. Right? This is the total energy at the point C. Must remember, we already know about the principle of conservation of energy. At every point, okay, let us say I have taken calculate the total energy at this point. The total energy at this point must be equal to the total energy at point C. Okay, that means at every point on this path will have the total energy conserved, right? Because no non-conservative force is acting. In the last class we saw, right? If the non-conservative force is 0, that means WMC is 0, then change of mechanical energy will also be 0. That means in the summation of potential and kinetic energy, there will be no change. This amount will be fixed. Do you remember?
Yes.
If I am going too fast, then let me know. Okay, I will try to go slower. Acha. So at C, we calculated the total energy. Okay. Now let us consider another point that has been shown here as D. Do you see the point D in the figure? They have
Yes.
taken it here. Okay, D, and they have considered the distance between O and D is x. Okay. So at D, what will be our total energy? Let us consider at D, the displacement x is equal to x as I have considered, and the velocity is equal to v. So at D, I know that P is equal to half k x square, and kinetic energy is equal to half m v square. So what will be the total energy? The total energy should be half kx square plus half m v square, right? Now the total energy at point C and total energy at point D, they should be equal to each other as per the principle of conservation of energy, right? So if I write it, what I get, this amount should be equal to that amount. Oh, sorry, এটা half k square মিটার a square ছিল, তাই না? কারণ এই যে এই পজিশনের জন্য x এর ভ্যালু তো a। I guess আমি ওই উপরের লাইনটা মুছে ফেলছি এজন্য। তো at point C, it will be half k a square, and at point D, the total energy is half k x square plus half m v square. তোমরা না বুঝলে আমাকে বলো প্লিজ, কারণ হচ্ছে এই যে তোমরা এটা আমাকে বলো না এতক্ষণ, তার মানে হচ্ছে তোমরা কিন্তু এই জায়গাটা বুঝছো কিনা আমার এখন ডাউট হচ্ছে। ভালো মতো খেয়াল করে দেখো, এই জায়গায় x এর ভ্যালু হচ্ছে a, because the displacement at point C is equal to the amplitude. বারবার বলতেছি, আমাকে যদি তোমরা না বলো যে বুঝো নাই, তাহলে কিন্তু এটা তোমাদের লস হবে। আচ্ছা, I'm waiting for you to ask me question. So from both sides, half and half we can cancel. So m, if I bring it in this side, it will be a by m. A square minus x square is equal to E square. So E will be equal to root over A by M A square minus X square. Now we know that root over A by M is equal to omega, that is the angular velocity. So if I replace it here, it will be V is equal to omega root over A square minus X square. This is the equation that we are trying to develop. Okay, that is equation number 5.29 in your book. Okay, so V is equal to omega root over A square minus X square. This equation we will be using to solve numerical problems, inshallah. Okay, সাদিয়া এখন বুঝতে পারছো?
Yes.
Okay, then C, we have conservation of energy in case of simple pendulum. Actually আমি তোমাদেরকে অলরেডি যেটা বুঝেছি না সেটা সিম্পল পেন্ডুলামের হিসাব করেই কাইন্ড অফ বুঝে ফেলছি, ঠিক আছে? তো যাই হোক, still let us discuss about it. Okay, and then inshallah from next class we will start power and efficiency. I hope in the next class we will be done with this chapter. Okay, so better before the next class, you start solving the numerical examples. Okay, then we can move on to creative. আচ্ছা, এই চ্যাপ্টারটা একটু ছোট ছিল তাই না? নিউটনিয়ান মেকানিক্স, ডাইনামিক্স, ওগুলো এটা একটু ছোট ছিল মনে হচ্ছে। আচ্ছা, so they have drawn a figure here. Let me draw it on the board, then I will start explaining. Acha, now this is the figure that is drawn in our book, and the topic is conservation of energy in case of simple pendulum. Okay, now to give you an idea beforehand, let me tell you this, or let me ask you, when the pendulum is in this position, what energy is there?
Potential.
Potential. Is there any kinetic energy?
No.
No, there is no kinetic energy, right? Okay, but if I leave it and it starts coming down at position C, what energies are there?
Here kinetic energy will act and potential energy will store.
Very good. Both potential energy and kinetic energy will be there. But the question is, there was no kinetic energy over here. But as it came to this position, some kinetic energy is there. So did we create some energy?
Potential energy টাই kinetic energy তে একটু চেঞ্জ হয়েছে।
Energy created.
Okay, the potential energy here, the total amount of energy was potential energy. And as it started coming down, see, it was at this level, it was at some certain height, right? It was previously at this position equilibrium, we took it to that position, so we have covered some height, right? So we can say that some potential energy has been stored in the body. Now as it is coming down, see, it is the height is decreasing from the equilibrium level, the height is decreasing, so the potential energy is decreasing. As the potential energy is decreasing, that decreased amount of potential energy is being converted into kinetic energy, using which the body is coming into motion, right? Now let us say the body came to this position. At this position, what energies are there?
Kinetic energy.
Only kinetic energy is there, because here it is at the equilibrium level. Okay, that means no height is zero, so that means the potential energy will be zero, the kinetic energy will be maximum. Okay, then what will happen, as it will cross this point, okay, the same story will be repeated. Now the opposite story will be repeated. The kinetic energy will now start to decrease as the velocity will decrease, and the decreased amount of kinetic energy will be converted into potential energy as it is covering some height from the ground again, okay, or we can say from the equilibrium level again, right? So what happens, maximum potential energy, minimum potential energy, maximum potential energy, minimum kinetic energy, maximum kinetic energy, minimum kinetic energy. Can I say like that?
Yes.
Okay, that's it. So let us go through. When a simple pendulum oscillates, the transformation of the potential and kinetic energies occur, as I explained, as you said actually. but at every moment the sum of kinetic and potential energy remain the same, which we already know, right? The summation of energy at this point and the summation of energy at this point will be equal. Okay, previously let us say potential energy is 20 and kinetic energy is 0 here. As it came to this point, potential energy has decreased. Let us say from 20 it decreased to 15, but we know that there is some kinetic energy here, and that kinetic energy will be 5 joule, right? We can say that because the decreased potential energy is the amount of energy that is being converted into kinetic energy. So 15 plus 5, that will be 20 again. So total energy 20, total energy 20, like that. And at this position, the potential energy will be 0 and the kinetic energy will be 20. So 20 plus 0 is again 20. So the summation of them is always remaining conserved. This is what we get to learn, right? Okay. Now let OA be the simple pendulum. OA is a simple pendulum. O is the point of suspension from where we have suspended the pendulum. Okay, and this is a rigid support. And B is the position of the pendulum at its maximum displacement. You can see B at the point B, it is the maximum displacement. Okay. At point B, the bob comes to rest momentarily. Momentarily means for a very short amount of time, just for a moment, I can say. It will come to at rest. That means the velocity will be 0. Then what will happen? Hence, at B, whole energy of the pendulum is potential energy, as we all agreed. Now the going of the pendulum from point A to B, from A to B, okay, means it's going from A to N vertically. Vertically, it is moving from A point to N point. See, vertically, it is moving from level A to level N, right? Hence, at point B, the potential energy of the pendulum is mg into vertical height. We know that potential energy, we are calculating this for point B. Potential energy is equal to mgh, right? What is the h? That is the vertical height. So, vertical height here, we all agreed that it is an. From A, it got up to n level. So, the vertical distance is an, correct? And m, we have considered the mass of the bob. The ball that we fix here is called bob. Okay, acha, bob. So at point B, the kinetic energy of the pendulum is 0, and kinetic energy is 0. So the total energy, let us represent it by T. It will be mg an plus 0 is equal to mg an. Okay. Now, let at any moment the oscillation, the pendulum reaches at point C. Now, as I have left it, it is coming down and it has come down to point C. At this point, the pendulum will have both kinetic and potential energy. Now, at C, the potential energy. At point C, we are calculating the potential energy mg into the height. From A, the height of point C is am, right? So, it will be mg into am. This will be the potential energy. Do you agree or not?
Yes.
Okay. The kinetic energy. What will be the kinetic energy? It will be half m v square. Okay. Now for v square, I can find an expression. See, v square is equal to, we know that u square plus 2g h. What is this h here? Always remember, I tell you always that whenever we are using h in case of calculation of potential energy, that is the height from the ground or the equilibrium level. But h that we use here, that is the covered distance, right? So here the initial velocity is 0 because we know that it is coming from B. The initial velocity was 0 there. Now 2g into h, that is the covered distance. What is the covered distance? That is mn. It was at n position. Now it has come down to m level. So the distance they have covered is mn. Okay. Now this mn, can I replace it by an minus am? Can I replace it? An minus am. Please let me know, did you understand? You understood this? Mn. This part I have represented as an minus am. Am থেকে যদি am কেটে ফেলে দিই তাহলে am ই বাকি থাকে. Anybody have any objection regarding this?
No.
No.
No? Okay, great. So we will replace the value of v square over here. So we will see that m into v square বদলে আমি কি বসাচ্ছি 2g into an minus am. Okay. Now 2 and 2 they will cancel each other and it will become mg an minus am. Okay, so we got our potential energy, we got our kinetic energy, so we can calculate our total energy for this point. So let us see whether it is equal to the energy that I got at point B. So total energy I represent by T. At first I will write the potential energy mg into am plus here it will be mg into an. At first if I take out the bracket mg into an minus mg into am, right? If I take out the bracket, you will see that mg am they will cancel each other and it will be mg an only. So we can see that the total energy at point B and point C they are equal. So we can say that we have proved the conservation law of energy in case of simple harmonic motion for a simple pendulum. Do you agree?
Yes.
Yes.
Okay. So hence they have written here, hence the pendulum obeys the principle of conservation of energy. If you want, you can put some values over here and then you can try to solve it. You will get the same value inshallah. Okay. So I can see that we have almost come to the end of our class. So inshallah tomorrow we will continue from the topic power and we will discuss about efficiency and we will be done with this chapter inshallah. Okay. So in the meantime, I would like to request you to go through the numerical examples that are here. How many? Only 24. Okay. Try to finish this at least up to 15 or 16 by tomorrow. Okay. Then I will tell you to go through the next, the rest of the numerical problems. Is the homework clear?
Yes.
Okay, thank you very much for joining. See you in the next class, inshallah. Before I end the class, anybody wants to ask any question? No? Okay, thank you very much. Assalamu alaikum warahmatullahi wabarakatuh.